Hello everyone. Today we are going to solve a question of calorimetry. Calorimetry means we are solving a question, a numerical, which involves heat or say energy changes. Okay. But there are a few things you need to know before solving such questions. Like first of all, you need to know what is a thermal equilibrium. What is a thermal equilibrium? See, if I have a system A, any system A, it can have anything. Like let us say it has water, it has 20 grams water. Okay. And we have a system B, which is connected to it, and it has, we can say alcohol, 30 grams. So if the both of the systems, if A and B are said to be in thermal equilibrium, that would mean that they both are at the same temperature. The temperature can be anything, but both of them have to be at the same temperature so that we can call them to be in thermal equilibrium. Okay. Now, more things you need to learn is heat is a form of energy. Heat is a form of energy and can flow from one system to another. So basically, if we have say two systems, one had water, one had alcohol, and they both are not in thermal equilibrium. Let us say the water is at 30 degrees Celsius, alcohol is at 10 degrees Celsius. So water has probably more heat in it because it is more hot, right? So water will, or let us just take water in both of them to make it clear. Yes. So system A is water, system B is also water. System A has water at 30 degrees Celsius. System B has water at 10 degrees Celsius. So what will happen now is the heat energy will flow from system A to system B, right? Because this has more heat, this has less heat. So heat can flow from one system to another. Whichever system will be having more heat, heat will flow from it to the other one, right? Next topic we need to learn is heat energy. Heat energy depends on amount of matter, or depends on quantity. Like let us say I have two buckets. I have two buckets. Both are filled with water. Both are filled with water, and has a temperature of both have a temperature of 40 degrees Celsius. But there is one slight difference, that the bucket 1 contains 5 liters of water and bucket 2 contains 20 liters of water. Is the temperature same for both of them? Yes, the temperature for both of them is exactly same. But if I talk about heat energy, the heat energy is not same for both of them. We can say that bucket A has less heat energy than this bucket B. Okay. Bucket A has less heat energy than bucket B because it has less quantity of water. Got, got my point? Now we upgrade our topics. We need to learn what specific heat is. Specific heat or specific heat capacity. Like let us say I have some water in this bucket. It is at temperature 20 degrees Celsius. I want to heat the water and bring it to 25 degrees Celsius. Now the question arises, how much heat do I need to give to the water? Okay, so we have a formula. The heat required is Q is equals to MC delta T, where Q is the heat required to be given to this water. M is the mass of water. Let us say we have 10 grams of water. So M would be 10 Now C is specific heat. For every material, it has a fixed value. Like for example, if I talk about water, the value for C is 4.184 joules per gram degree Celsius. That means I will just put this value over here, 4.184, and delta T, that is the change in temperature I am wanting. The change in temperature I want is how much? Final temperature is 25, initial temperature is 20. So the change would be of 5 degrees. So I can calculate from here how much total heat will I be requiring for this specific conversion, for taking 10 grams of water from 20 degrees Celsius to 25 degrees Celsius. Okay. So from this example, we need to know what specific heat is. It gives us an idea of how much heat is required, for any substance, in this case water, to raise its temperature by some degrees if we are aware of the mass of substance. Okay, like I can say for raising temperature of 1 gram water by 1 degree Celsius, 4.184 joules heat is required. I hope you get this. Okay. Now to our last concept for now, and then we start our question. This is latent heat of fusion. This is latent heat of fusion, or we can say enthalpy of fusion. Enthalpy of fusion makes it clear that if we are converting ice at 0 degrees Celsius to water at 0 degrees Celsius, we would need to heat the ice. And the heat energy required here would be equal to mass of the ice we are taking, whichever ice we need to melt, multiplied the enthalpy of fusion, which is denoted by delta H and a F in the subscript. Okay. So this delta HF also has a fixed value. If I'm talking about water, this value goes like 334 joules, 334 joules per grams. In this, you can see that the temperature is not changing. When we talk about the latent heat of fusion or enthalpy of fusion, ice is getting converted from ice at 0 degree to water at 0 degree. There is absolutely no temperature change, although some heat is involved. Okay. Now let's move to our question. Yes, we have this question. It says a 5-gram sample of ethanol goes through combustion in a container submerged in 2 liters of room temperatured water. What this means is, let us draw a small diagram for this. This is a very special question and a very advanced question of calorimetry. It says we have a big container. It is a closed container and it has a small vessel inside it. It has a small vessel inside it, and the rest of the container is mostly filled with water. The rest of the container is mostly filled with water. Now, in the small vessel we have, in this small vessel, there is 5 grams of alcohol, 5 grams of alcohol, which is undergoing combustion. So it will obviously produce a lot of heat energy. Okay. Now this heat energy will be produced in this vessel and it will be transferred to this water outside and it will heat up the water. Okay. So now we know that eventually all of the things in this whole system will be in thermal equilibrium, meaning that they all will acquire same temperature. All of that will acquire the same temperature. So this is a special container, and we know that this container and the water inside it both will get at the same temperature when this whole thing ends, because the container and the water will be at thermal equilibrium. The container and the water will be at thermal equilibrium when this heat is going out of the vessel. Okay. Right now, initially, we are given that the water is at 20 degrees Celsius and the container is also at 20 degrees Celsius. That is the room temperature given to us. Okay. We can be sure of one thing, that in our question, we will be getting a temperature which is more than 20 degrees Celsius, because the ethanol, which is ethanol or say alcohol, which is getting combustion in this small vessel, will be giving out heat, and that heat will warm up the whole substance. Okay. So first of all, let us calculate that how much heat is being produced. First, we will calculate that how much heat is getting produced. If we read the question correctly, it says the enthalpy of combustion of ethanol is minus 29.7 kilojoule per grams. Now, what does this mean? Enthalpy of combustion of ethanol is 29.7 kilojoules per gram. It means heat given out by burning or combustion, by combustion of ethanol is equals to, with a negative sign we write this. See, whenever heat is getting out, heat is getting evolved to by the system, heat is getting out of the system, we put a negative sign over it. Okay. So the vessel is giving out heat, so it gets a negative sign. Now this heat is for per grams, yani for 1 grams. It is for 1 gram. In total, we have 5 grams. So total heat given out would be equal to minus 29.7 kilojoules per grams into 5 grams. The grams and grams would get cancelled, and we would get minus 29.7 multiplied by 5. That would give us negative of 148.5 kilojoules. Yes. Don't forget to write the unit behind that. Okay. So this much heat energy we are getting from the ethanol. Now, this heat, this or say this energy will be used up, for heating the water as well as the container. This energy will be used up for heating the water as well as the container. Okay. Now, one thing we can say is that both of them, the water and the container, will be in thermal equilibrium. To be in thermal equilibrium, they have to reach to the same temperature. Initially, both of them are at 20 degrees Celsius. But finally, they will be getting to a temperature and both of them would be getting to the same temperature. Like, let us for now assume both are getting to 30 degrees Celsius. Okay. So the change in temperature for both of them would be same. The change in temperature for both of them would be same. So we can write the change in temperature delta T for water would be equal to the change in temperature for the container. I really hope it's clear till here. If it's not, I recommend to pause the video, rewatch it, read the question carefully, and then proceed further. Okay, so we know that the alcohol, the ethanol, is giving out this much heat, negative of 148.5 kilojoules. That heat is being used for warming up, for heating up the water as well as the container. Both of the water and container reaches to a same temperature value. But the fun part here is that both of them will not be absorbing the same amount of heat energy. They will be absorbing different amount of heat energy, but they will be reaching to the same temperature. Now let's see how that plays out. For delta T water, we have the formula Q is equals to mc delta T. That is, the heat absorbed by water would be equal to the mass of water. Now, do we know the mass of water in this question? If you read the question again, it says 2 liters of water. Now, 2 liters of water would be equal to 2000 ml of water. And I must tell you that 2000 ml of water just weighs 2000 grams of water. Okay, like 1 ml equal 1 grams. That is from the density of water. You can just remember it like that. 2000 ml of water equal 2000 grams of water. So the mass of water we have is 2000. The specific heat, the value of C for water that would be given in your question is 4.184 joules per grams degree Celsius. So let's just write the value over here, 4.184. And the delta T, that is the change in temperature. This becomes our equation 1 for water. Now for the container, we write a similar equation. First, read the question again. It says, if the container absorbs 2.30 kilojoule for every degree Celsius temperature change, which just means that heat capacity of the container equal 2.30 kilojoule. So then we have to find out what is the final temperature of the water. The last line tells us that for the container to get every 1 degree Celsius rise in temperature, it would need to absorb 2.30 kilojoule. Like for 1 degree rise, it would absorb 2.30 kilojoule. For 2 degree rise, it would absorb 4.60 kilojoule. For 3 degree rise, it would absorb 6.90 kilojoules. Are you getting that? So we can form a formula here which would say heat absorbed by container would just be equal to the specific heat we have. What was the value? 2.30 kilojoules, right? This 2.30 kilojoules multiplied to how much temperature change we need. How much temperature change we need. And this gives us our second equation. Now be very careful about it that the delta T in both the cases is exactly same. If you have any confusion over it, go over the video again. Okay. So delta T is same for both of them, but the Q water and Q container are not at all same. They are two different things. But where is this heat coming from? The water is absorbing heat and the container is absorbing heat. They are both getting this heat from the combustion of ethanol, remember? So we can say the heat evolved by combustion of ethanol would be exactly equal to the heat absorbed by water and the heat absorbed by container. They both will be absorbing all of that heat. Okay. Now We knew this value, we calculated this value, remember? This value came out to be negative 148.5 kilojoules. Negative 148.5 kilojoules. It is equals to Q water. Just write this whole equation here. 2000 into, or you can multiply that. I'm just writing the equation. Do the calculation on your own, okay? This would be like this, plus the heat absorbed by the container, that would be 2.30 into delta T. Now this all would give us the total heat which is getting released by the combustion of ethanol. From the right hand side, from the RHS, what we can do to ease out the calculation is take the delta T common, because it has a plus sign in between. So we can take the delta T common. It would be 2000 times 4.184 plus 2.30. Then multiply these two, add to this one, then divide it by taking to the left hand side, and you'll get your change in temperature. That change in temperature would be for both. It would give us the change in temperature for both water as well as container. Because both of them are getting equal change in temperature. Okay. Now the final question was, what is the final temperature of the water? So how will we find out the final change? Let us say that delta T comes out to be 11 degrees Celsius. So that would mean a 11 degree Celsius rise is observed. So if we had the water originally at 20 degrees Celsius, our water would be at 31 degrees Celsius at last, and that would be our answer for this question. And although this is not the correct answer, I just supposed this. I didn't do the actual calculation. I'm leaving it to you guys. I want you to solve this correctly and drop this in the comment section. Okay, I'll then mark your answer right if it's right, and I'll mark it wrong if it's wrong. Okay, so that is one question of calorimetry. If you have any other ones, stay tuned, or you can drop a question in the comment section. Okay, bye bye, all the best. Thank you.